when I'm looking at these equations here, if I've got like y equals 2 sine x plus 1, the trick part here is, well, I can't really use dilation reflections and transformations to figure out the x-intercepts. I mean, yeah, if I've got like an equation like this, it's like, well, if it was just y equals 2 sine theta, well, I know that, oh, sine theta is, your y coordinate, right? So we're going to start at 0, go to +1, end up on, again, back to 0. So it's going to be a bit like this. This hasn't been dilated from the y-axis. It's only been dilated from the x-axis. So I know this is going to be a point of 2. That's going to be my intercept, right? That's going to be -2. This is going to be pi. That's going to be pi on 2. And that is going to be also 2 pi. That's going to be 3 pi on 2. And so on. So I can actually see, where this graph is. However, if it's been translated 1 up, the graph's going to be like, the graph itself, it's still going to be there, but it's going to be kind of like here. And I don't know where these intercepts are. I know this would be 3, and I know this would be -1. But like where my original peaks were are kind of occurring here, here. I know where my peak and trough is, but I don't know where my x-intercept is. So with this, I would need algebra. Okay, I'd need to let x equals 0, y equals 0, because that's what we always do to find out your x-intercepts. And it's going to be 2 sine theta plus 1. All right, -1 equals 2 sine theta. And then I've got -1/2 equals sine theta. Now I know when sine theta equals -1/2, that would be at, well, when it equals 1/2, it's going to be pi on 6. So for it to be -1/2 would be here and here. So that's actually going to be at 7 pi on 6, and 12 pi on 6 minus 1 pi on 6 would be 11 pi on 6. And then we can, use all the times from that. So I know now that is 7 pi on 6, okay, and 11 pi on 6. So with the next subchapter, you're going to need to use this method. You still can use this method for it. It is perfectly fine. So to find my y-intercepts, I mean, I can let y equal 0. But you'll find, actually, sorry, you can't really do it. Well, I'll show you why. Because if you want to let x equals 0, y equals 0, you've got then equals 2 sine theta. You can do it, actually, sine theta. Divide by 2. Well, it's going to be 0 equals sine theta. Well, when does sine theta equal 0? Well, it equals 0 at, 0 radians, and it will also equal 0 at pi, and 2 pi, and 3 pi, and so on. So you can use this method as well to find your x-intercepts. However, it can be a bit cumbersome and take you a little while. So feel free to use this method if you want to. It will work for both of them. Alternatively, another method you can use is just by understanding how the dilation, transformation, and reflections will occur. So that's kind of 14J, okay? When it's being translated up or down, how do you find those x-intercepts? We also need to take into consideration if it has been dilated from the y-axis, and we will look at that again next lesson. But going back to if it hasn't been translated in the y-axis, you can do it just through thinking of your dilation, reflections, and transformations. So we've got 3 sine theta minus pi on 2. So I've got a graph of y equals 3 sine theta minus pi on 2. So the dilations is 3 from, that's going to amplify it, x-axis. It hasn't been dilated. There'll be a number out here if it's been dilated. And remember, if that was like 2, for example, it would be dilated by 1/2. Has it been reflected? No. No reflections out the front here. No reflections in here with that one. Has it been translated? Yes, it has. It's been translated by pi onto positive, that is. That's just my dash. Positive pi onto in x-axis. And not in the y-axis. Now, if it's done in the y-axis, I probably can't do this. So what I can do, right, is I can just draw a sine graph. Now, I know that if you think about it, it's been dilated by 3. So really, it's going to be stretched up and down. Now, it hasn't been dilated this way. If it has been dilated this way, I can start changing my numbers. So what's happened though is it's moved plus pi on 2. So instead of it normally the axis occurring here, the whole graph has been shifted. Sorry, let's choose this point here as my axis. So if my axis went through here originally, the whole axis has actually been, the whole graph's been shifted pi on 2 across. Now pi on 2 is actually here. So I know my axis is going to be there now. Okay, it hasn't been moved up or down. I can put that right through the middle. That should be through the middle. Sorry about my rough drawing. It's not very good. So now I can know all my points. So originally, you know, that now is 0. And originally, remember, pi on 2 would occur up here, but that's obviously going to be pi on 2 plus pi on 2, so that's going to be pi. This is going to be pi on 2. This is going to be 3 pi on 2. That's going to be 2 pi. And so on. You can just keep on adding your halves. So that would be the easiest way. Don't forget about your amplitude. Easiest way to draw them. Thinking about dilation, reflection, and transformation. So if we've got 2 sine 3 theta plus pi on 4, that was 3, wasn't it? So we're going to do our dilations first. 2 from x-axis. A third from y. No reflections. Translated. Negative pi on 4 in x-axis. So, how do we go about doing this one? Draw a sine graph. You might need to do a couple of them sometimes, just because it does get a bit messy. And you'll probably see what I mean by this one. So the first thing I'm going to do is my dilations. Now, obviously, I haven't taken the domain into consideration, but that sort of will be implied a bit later. So I know it's going to be 2 here. Now, it normally occurs at, this would be pi. This would normally be 2 pi. This would normally be, obviously, 3 pi on 2. And this would normally be pi on 2. So that's a bit better. Now I can zoom in. And so on. Now, what I can do to these values is I know it's gone a third in, right? A third from the y-axis. So really, I just need to multiply each of these now by a third. So I need to now multiply each of these by a third. So really, I now know that this point here up the top is actually going to be pi on 6. This point here is going to be pi on 3. This point here is going to be, that was 3 pi on 2, so that's going to be 3 pi on 6. This was 2 pi, so that's going to be 2 pi on 3, and so on. You can do all of them if you like and just keep on going along with that. So now you've got the idea of how we can translate them. Now I need to move all my points pi on 4 across in the net goes negative in the x-axis. So the whole graph is now going to go across. So what I tend to do is I actually don't quite do it like this. I'm just trying to give you guys a bit of an idea. I would actually write out my values here. 0. That's pi on 2. That is pi. And I should just draw my graph again. Let me just draw it a bit spaced out because I'm not really enjoying this. So what I mean by this is let me just try and scribble this out. I don't want to do that. I want to do the eraser. So how I would go about this, I need a bit more space. And you can go on for ages. But clearly here, you would be starting off normally at 0, pi on 2. That would be pi. this would be then, I should have written it down further. Here we go. 0 pi on 2 pi would be at this point. So I'm talking about these points. And you can keep on going. This is going to be 3 pi on 2. This is going to be 2 pi. This is going to be, that's going to be 4 pi on 2, 5 pi on 2, 6 pi on 2, which is 3 pi. So the first thing is we did dilation in the x-axis. Don't worry about the amplification because the amplification of 2 is going to change that from 1 to 2 and -2. But then we shrunk it all by a third. So I'm going to multiply each of these by a third. So that's still 0 pi on 6. So we're dilating by a third from y-axis. That's going to be pi on 3. That's going to be 3 pi on 6, which is going to be pi on 2. That's going to be 2 pi on 3. I should keep these level. That's going to be 5 pi on 6. And this is going to be pi. Now we've got to translate all my points by pi on 4, and I think it was pi on 4 in the negative axis. So I've got to now minus pi on 4 from them all. So it's going to be 0 minus pi on 4, negative pi on 4. This one's going to be hard because I have to find my common denominator, and that gets really annoying. So it's going to be pi, that's going to be 12. So that'll be 2 pi on 12 minus pi on 4, but in terms of 12 will be 3 pi on 12. That'd be 4, 8, 12 again. So that would be 3, 4, 3, that'd be times by 4. That'd be 4 pi on 12 minus pi on 12. Minus 3 pi on 12, I should say. This would be in terms of, well, this one, because I'm only translating it by pi on 4, the easiest would be, that would be 2 pi on 4 minus pi on 4, and so on. You can do all of these, right? So that's going to be then you get to your final answer, and you can do it like that. Okay, so then I know where each of my points are, and I can figure that out. Now, sometimes it's quicker to do it this way. Other times, if you just need to find your x-intercepts, I would go about it the other method that I show you. So you're going to know this point's going to be minus pi on 4. That's going to be minus pi on 12. That's going to be pi on 12. And this point here is going to be pi on 4. And now I can just sort of see, once you've got your sequencing there, I know, that obviously every gap is changing by 2 pi on 12 or pi on 6. Okay. So I can see that, every time I'm actually adding from point to point, because it hasn't been dilated, it hasn't been translated or up or down. I know that each of these points, because I've chosen sequential points along here, the difference between them is, sorry, no, it's not. It's, what is the common difference? Yeah, the common difference would be 2 pi on 12, I believe, on there. So you can see now we can just keep on adding the period and keep on repeating that one along. So that's where we're going with this one. You can sort of work them all out through that. Once you've got a cycle done, though, you can use the repetition of your cycle because you know the difference between them all. And really, that's pretty much it with those ones. So 2 pi on 12 is, what's that? It's pi on 6. So if you go pi on 4 plus pi on 6, where would that take you? That would be, you'd have to go to 12, so that would be negative 3 pi on 12 plus it would be 2 pi on 12, right? So that takes you to negative pi on 12. Here, if you add 2 pi on 12 to that, it's going to take you to pi on 12. If you add 2 pi on 12 to that, that's going to give you 3 pi on 12. That's going to simplify down to pi on 4. Plus 2 pi on that's going to be 5 pi on 12. So it'll be your next point. Plus 2 pi on 12 on top of that would be 7 pi on 12. plus 2 pi and 12 on top of that would be 9 pi and 12, but 9 pi and 12 will simplify down to 3 pi and 4. Plus 2 pi and 12 and 9 pi and 12 would be 11 pi and 12. And therefore you can get your whole cycle going on, because now I know where that is. So you just sort of need that first cycle to figure out how far each of the gaps are, and then you can label all your points on there. And then you can just draw it according to where the graph is. Yeah, so that's pretty much it where you're going with those. There's the two strategies. The other strategy for this graph, which might be a bit easier, would be to just, on this graph, you probably would let x equal 0. You may do that, but you got to let this thing equal theta. The problem here is sometimes you can't. You could let that whole thing equal theta, and when you want to find it when it equals 0, and then you can undo it. I would probably go that method. So I'll show you this method here, just another method. So it depends on how complicated it is, and you will have a go at those. So another thing you could do here is you could do y equals, we're just going to write it out, 2 sine 3 lots of theta plus pi on 4. So I want to know the x-intercepts, for example, is 0, okay? And let y equal 0. So I'm going to go 2 sine 3 theta plus pi on 4. I'm going to let, let's say a equal 3 bracket theta plus pi on 4. So we're going to say, well, when does 0 equal 2 sine a? What you're really saying is, I'm going to divide both sides by 2. So it's just going to go, hey, when does sine a equal 0? Well, that means a will equal 0 when, obviously, we're talking about the unit circle, sine, talking about these points on the graph here and here. So it's going to be at 0, pi, 2 pi, 3 pi, 4 pi. That's what we realized here. 0, pi, that's when it equals 0. 2 pi, 3 pi, right? But we know we let a equals 3 theta plus pi on 4. So the first thing you're going to do is divide by 3, which is the first thing you do here. You always do your dilation, then your reflection, then your transformation. So we're actually going to divide each of these terms by 3. 0 divided by 3, whoop. And this is the method I would use, is going to still be 0. That's going to turn into pi on 3. That's going to turn into 2 pi on 3. Whoops, sorry. I've jumped the gun. This should still be pi, 2 pi, 3 pi, 4 pi. Because now I need to divide by 3. So that's going to leave me with theta plus pi on 4. So that's going to equal 0 still, pi on 3, 2 pi on 3, 3 pi on 3, which is just pi, 4 pi on 3. So notice when we dilated them, we've still got 0, pi on 3, 2 pi on 3, and pi, which is this one. Then what we did is we then translated by negative, in the negative axis by pi on 4. Well, we're going to take away pi on 4 for each of these. So it's the same thing. One's just doing it manually. The other one, I would probably go with this. So theta equals, we've got a minus pi on 4 from each of these. Negative pi on 4. A third minus pi on third. We've got to change that. We've already done the thinking of this one. So I'm just going to say it's pi on 12. Because you've got to get the same common denominator. 2/3, that will turn into 5 pi on 12. And pi would turn into 3 pi on 4. And so on. And that's how you can get them. Now you know where your x-axis is. So now you can draw your sine graph, right? And you know that you're going to have all the different points. So you can put those on the graph and figure out where they are. Personally, I'll probably make them back into 12ths so you can spread these out easily. So I'll probably make that back to 3 pi on 12. That's pi on 12. I would write them like that on the graph, but this just gives me some idea of where the graph is occurring. That's going to be 4/8. That's going to be 9 pi on 12. So I know that's been translated by pi on 4 backwards. So here's a bit of the tricky part about trying to figure out where, and that's going to be negative, where the axis is. So from 0, it's actually starting at negative 3 pi on 12. So this point here is going to be minus pi on 4, right? And then it's pi on 12 here. That's pi on 12. Now, if you think about what's actually occurred here, if you look at this, we've got 4 pi on 12 here is the difference. So we know that the axis is going to be, if you go 1, I can split this up into quarters, 2. So we've got 1, 2, 3, 4. I know that the axis will go through there. Okay, because that's minus 3 pi on 12, that's pi on 12. Then I know this point here is going to be, and that's this point, by the way. This point here, and I should write them as coordinates, is 5 pi on 12. And then this point here is going to be 9 pi on 12. Now, if I want to find my midpoint, well, I know what's halfway between pi on 12 and 5 pi on 12. 4, 2, that's going to be 3 pi on 12, right? Which is 3 pi on 12 is actually, I can simplify that down to 3 pi on 12 is going to be pi on 4. Now, remember, you shouldn't write them there. You got to write them simplified. So that would be why that works. Again, halfway between these 6, we can go 8. That would be 7 pi on 12. So here would be 7 pi on 12. And you're going to always write them as coordinates if you've got to write the peaks and troughs. Don't forget it had an amplitude, I think, of 2. So that's going to be comma 2. And that one here, that would be down here as well, negative 2. So you've got to think about where the graph's been translated on here, because some people can draw this wrong. They might have actually translated it too far and done a graph, like inverted it, reflected it. So that's the one thing you've got to be tricky, a bit confident about. If you're just doing like this, where you're trying to find the solutions, you've got to know where the graph, how much it's been translated back, and do that consistently. Whereas if you go with this method, you're actually going to be able to see from your graph, because you started with an original graph and then you dilated, translated, and so on, you can actually figure that out. You still can do the same thing here. You could technically, what I would do for you guys is just think of, well, when it's 0, well, if it's starting here, you can actually graph it like this. So that is reaching 0 again. Then it reaches 2 pi. Then it reaches 3 pi. Then it reaches 4. So you know that each of these points will relate to that. But the trick here is then it goes back pi on 4. When it goes back pi on 4 and you've dilated it, it already that's where it gets a bit confusing for you. But that would be it. So have a crack with a few of those. And hopefully that will help you guys.